Alrighty. Now that we understood indexing in the last one, let's try to understand normalization in this video. If you've done DBMS in a computer science class, you've learned much more than what we're discussing today. If you haven't, then you learn a few new concepts, which, if I'm being honest, you can arrive at from first principles as well. As we go through this video, you'll realize, acha, this sounds fairly obvious and simple to me. I don't know why I had to learn normalization for this. Whenever I think of solving a problem, whenever I think of designing my schema, I would have always done it in a normalized way, Harkirat. So I don't know what's the point of learning this, and that's true. You learn normalization purely for people who are currently struggling with database design. For example, if I ask you, okay, give me the database design of a medium like app, so it should be fairly obvious to you. Maybe not actually. It depends on when you started to create full stack applications, but it might look something like this. Okay, there's a users table which has username, password, first name, last name, and email, things like these, and then a separate table called blogs or posts, which has this user ID has made a post with this title and this description, and this was the time at which this post was made. You would create two separate tables, a users table and a blogs table. You would most probably not do this. Okay, Harkirat, I will create single table called users and blogs, and here, Harkirat, I will have this also, and I will have this also, and I will have multiple entries for the same user. You wouldn't do that, right? You wouldn't create a table that looks a big table like this. Catch this table, users and blog, will look like this. Okay, Harkirat with the password 123123, with the first name Harkirat, with the last name Singh, with the email harkirat@gmail.com, has made a post on with the title, user IDs, whatever user Harkirat's ID, which is let's say 1, with the title my first post, and with the description, some long description, at some 20th April. You will not make this sort of a database schema. Single post I will create Harkirat, and if Harkirat creates single table I will create Harkirat, and if Harkirat creates another post I will create another entry where the first set of rows will remain the same and the second set of rows would change. This is the second blog post, so it will be my second blog post. It will probably be published on 21st of April, so on and so forth. I'm assuming you from first principles understand. Yeah, this looks very wrong. Even though this might just work, when Harkirat signs up, I will put an entry here and keep everything after this null, something like this. And then when Harkirat makes his first post, I would probably just put the entry here. When Harkirat makes his second post, I will make another entry for Harkirat and copy over all the metadata for Harkirat here and blog posts here, and then third one I'll do the same. There are a bunch of problems here. Number one, you're repeating a lot of data. There is a lot of redundant data. In every row you're storing my email when you should only store it in one place. Number two, if Harkirat tries to update his first name or last name, you have to make those updates everywhere. So you have to touch a bunch of rows. Even though Harkirat has only changed his name once, you change 10 rows and change his name over here, which is why you always normalize your database. What do? You break them down into smaller tables so that if Harkirat ever changes their name, he only changes it in one place. If Harkirat ever adds a blog post, he just adds the blog post data. Of course, these tables are related somehow, but they are what? They are normalized. They are broken down into smaller tables that are somehow connected to each other. That is generally what normalization means. When you are in a DBMS class, in a computer science class, they'll give you a table like this and say, okay, normalize this table. Tell me what's wrong in this table. And why is this not normalized? How do you make it normalized? And then you're supposed to, write explanations as to why this is not normalized. Okay, there's a lot of redundant data being stored here, which is why you would not have a database like this, but two different, a table like this, but two different tables like this. So that is what data normalization means. Now let's understand it, more practically. Okay, what does normalization do? Harkirat, you told me it lets you convert from this to this. Yes, but how? I was able to do this from first principles. But you can figure out rules on which you're able to figure out that this is not normalized and this is normalized. What are those rules? Let's understand that. What is normalization? To recap again, normalization is the process of removing redundancy in your database. What is redundancy? Redundant data means that the data exists somewhere else and we are duplicating the data in two places. For example, if you have two tables, one called users and one called users metadata, let's say, where you do the following. Well, this is wrong. This should be the orders table. So a users table and an orders table. Then it might look like this. Here users table has user ID, username, password, and name. Two users I have, Kirat, full name Harkirat, this is the password, Raman, full name Raman, and this is the password. And I have a separate table called orders. Okay, these are the Starbucks orders. Let's say this is the Starbucks database. So these are the Starbucks orders that Harkirat has made. Harkirat has made two orders. One, this order for rupees 300, one, this order for rupees 200. Raman has made one order. But notice, along with order ID, user ID, and amount, I also store the name here. You might do this sometimes if you're just beginning to code. When you just begin to code, you put data everywhere. Yeah, let's just keep it. What if we need it? You might think, okay, Harkirat, the Starbucks receipt that the user gets, only has the amount and the name of the person. So, storing the name here is a good idea because I can just hit a single row, get this row back, get the amount and the name, and show it here on, on the website, on wherever the user is tracking their order. But again, the problem here is there is redundant data. You have stored the name here twice when it already exists here. This should be the source of truth. You already have the user ID here. It already says that this order is for Harkirat, whose ID is 1. So why not get his data from this table where the source of truth exists, where his first name exists right here. So that is why you would want to normalize this and not store name over here, but have just the user ID and relate the data through the users table. Reasons remains the same. Okay, if Harkirat ever updates his name, we have to update it here, we have to update it here, we have to update it 10 different places. Versus if we had a normalized database, if the query that wants to get this card for a user with the amount and the name, if it hit this table as well as this table, got back the first name of Harkirat as well as the order details, then this would be normalized. Then there would be no redundancy in data. Again, do you understand redundancy? Redundancy means you're duplicating data, and if some query goes wrong ever, you might overwrite the name here. Harkirat becomes Raman, or Harkirat becomes Kirat, but it remains Harkirat here, remains Harkirat here. Your data is completely inconsistent. It leads to a lot of errors in case you have redundancy in your database. There is no downside of duplicating data. Sure, you can actually save some query time here because you're hitting a single table versus hitting two tables, but you avoid redundancy in most cases. 99.9% you will not duplicate the data here, so that this query becomes faster and you don't have to hit the users table. You don't have to join the tables somehow to get the data. You don't do that usually, which means this row here is probably wrong. Shouldn't have it here. What should we have? Order ID, user ID, and amount. And of course, the user ID is here, username, password, name, whatever we need for a specific order can eventually be fetched from this table. Okay, order ID 1 details are needed. So, okay, order ID 1 is for user ID 1. The name is Harkirat and the amount is rupees 300. That is what redundancy means. If you notice, we have stored the name on the order in the orders table when it is already present in the users table. This is what redundant data means. Notice that the schema is still foolproof. We can get the order given a user's ID. We can tell the user's details, name, first name, last name, given an order ID. One more thing to notice here is, even though there is redundancy, we've put the name here, we have also put the user ID. So let's say if the card required not just their name, but also their username, you can still fetch it from this database. It's this table. It's still foolproof. By foolproof, I mean, even though you try to, dump some extra data here, you still have the user ID, and hence if needed, you can always go to this table and get the name of the user, get the password of the user, let's say if you need it, or get the username of the user. It's still foolproof. What is not foolproof? A schema that looks like this. Let's say you don't store the user ID here. You are like, array, card only needs the amount and the name, doesn't need the username. So why do I have to store the user ID of the user in this table? I will not store it. I will simply store whatever this card needs, which is name and amount. Given an order ID, let's say 1, I just need the amount of that order and the name of that order. And hence I will simply store the amount and name over here. I will not store the user ID for whose order this is. What is the downside of this? Can you think of it? This looks great, right? Theoretically, it looks great. The card only needs this much. Why do you need to store the user ID here? And the answer is, what if in the future you also have to show the username here? There is no relationship that you have described. You have written that order 1 was placed by Harkirat, but how many Harkirats? There might be 10 Harkirats in the database. How will you in the future ever relate this data? You might be like, Harkirat, I don't want to relate data only. This is good enough for me. Sure, you can say that this is good enough, and whatever I needed I have dumped in this database. But this is just a dangling order. This order is not related to any user, or it actually is, but you haven't stored that relationship. That data is lost. Whenever the user came to your website and placed an order, you should have at least somewhere stored this order ID 1 is for this user ID 1. This order ID 2 is for this user ID 2. You skipped that altogether because you are a young developer just learning, and you thought Harkirat, the name and the amount is only needed in this card right here. So the name and the amount is what I will store. That is bad. So what did we learn? We learned at the normalization has nothing to do with foolproof data. This data doesn't have any relationship between orders and users. This is just plain wrong. This you should never do only. You can never tell the orders for a user, especially if 2 users have the same name. If 2 users have the same name, and let's say after 1 year I ask you who placed this order, you will not be able to tell if this was this Harkirat or this Harkirat. You never stored that user ID mapping over here. Normalization is done on tables that are foolproof, in the sense that this is plain wrong only. Normalization has nothing to do with this. It has your data is foolproof. You still have all the relationships, but you're still storing some extra data here. So how can you get rid of this extra data? That is what normalization lets you do. Before we proceed into normalization, let's quickly understand relationships one more time. We have done this in the past. There is a specific video on relationships in Postgres databases, so you can go through that. But a quick refresher, there are 4 types of relationships usually in databases: one-to-one, one-to-many, many-to-one, and many-to-many. Let's take a simple example and understand this better. Let's say you have a library management system in which you're storing 4 tables. A users table, which will store all of the users that have signed up on your application, on your website, let's say. Library card table. Let's say the users can also issue themselves card, like enrollment cards or physical cards. So a table that tracks all of their, card IDs, card RFIDs, address to ship it, so on and so forth. A books table that has all the books that this library currently has, and a genres table. These are the genres for a book, for example, this genre, whatever you want to call it. It means, is it a horror movie? Is it a thriller movie? So on and so forth. Let's understand how this table would look like, and specifically the relationships between them. Would they be one-to-one? Would they be one-to-many? If you have not gone through the relationships class also, this should be fairly easy to understand. One-to-one probably means every row here is only related to a single row here, and vice versa. You can never have a single row related to double rows over here, or vice versa. Let's understand that with the library card and the users table. These are the users that have signed up on your website. Let's say there are 2. Both of them have the same name, should have different IDs. This is wrong. This should be 1. This should be 2. And password is 1, 2, 3, 4, 5, 6. Let's say the password is also the same. Again, this ID should be 2 over here. The library card table has an ID of its own, a user ID. This specific library card is for ID with a user with ID 1 and 2. And lastly, a card number, which could be, a random number that you issue for every user. Notice this data, and this data is related. This user ID, this library card is for user ID 1, and a single user can only have a single library card. You're not allowed to issue multiple. You're allowed to issue a single library card. So a single user will never have 2 entries here. There will be no 2 rows which have user ID 1, and vice versa. A library card is for a single user. This user ID field is a single, right? You can't store 1, 2, 3 over here. So you can never have a single row that's related to 2 rows on the left. That is what one-to-one means. What does one-to-many mean? Again, it should be pretty straightforward. This is probably a bad example. A better example is, posts table that we just discussed. Okay, this is the users table, and this is a posts table. And every user can have multiple posts. A user can have, a blog post for a Medium-like application. Let's say you're creating something like Medium, which we have in the past. A single user can have multiple posts, 1, 2, 3, and then the second user can also have 2 posts, so on and so forth. So this is a one to many relationship, which means, a single user can have many posts, but a single post, a single row here is associated to a single user over here. That is why it's one to many. This specific post cannot have multiple authors. You might say, Harkiyat, my Medium app can have multiple authors. Yes, then it becomes many to many. But our restriction is that a single user only has a single post. Sorry, a single user can have multiple posts, but a post only has a single author, which is why it is one to many. But if you do add the restriction, here a single post can be written by multiple people, then sure, then it becomes many to many, which is a single user, let's say user ID 1, wrote a blog post on CS fundamentals, then and another user is a co-author of it with user ID 2. Then yes, of course, becomes a many to many relationship, that a single CS fundamentals blog post has been written by 2 authors. What does that become? That becomes many to many. When does it remain one to many? When a single post has a single author. But right now, as you can see, it has 2 authors, which is why it is many to many. Another example here was the library example. Okay, let's say a user can check into a library and check out of a library. Let's say it's a physical library. Then the check-in time and the checkout time is what you're storing here, let's say. That will also be one to many. A single user can check in multiple times, but a single check-in is for a single user. You cannot have a check-in for multiple users. Okay, 2 people checked in together, so I will have a single row here. No, you have a row per check-in, and every row is uniquely associated to a single user. A single user can have multiple rows on the right side. Many to one is just the opposite of it, which basically means if I put this over here, it becomes many to one. A lot of times, I couldn't think of a good use case here, which is why I left it empty and just said, very good. It's just the opposite of the thing above. But if you understand one to many, you probably understand, it'll be very easy to understand many to one as well. Okay, whatever is the thing on the left can be related to multiple things on the right. Sorry, vice versa. Whatever is, you get the idea. The opposite of this. What is one to many? The thing on the left can be associated with multiple things on the right, but the thing on the right can only be associated with a single thing. If you look at this row, it is attached to a single user with ID 1. If you look at this row, it is attached to a single user with ID 1. This is the check-in of user 1 at 10 a.m. This is the check-in of user 1 at 2 p.m. None of these are related to user 2. You cannot have a single row associated to both of them. And similarly, many to one is just the opposite, which basically means just put this on the left, put this on the right. That's many to one. So one to many to one can be used sort of interchangeably. Many to many, as I discussed in this blog post example. Similarly, you can have, the genres table. Okay, a single book can have multiple genres. For example, this Harry Potter book that I have is just a horror movie. But if you look at the 5.someone movie that I have here, that is both a horror movie as well as a thriller movie, which is why this can be associated to multiple rows. A single book can have 2 genres, and a single genre can be associated to more than 1 books, is what makes it many to many. If a single thing here can be associated to multiple things here, which is this last row here, that's many on the left and or whatever on the right. And then similarly, horror over here is related to this guy and this guy, which makes the other side many as well. And this is a many to many relationship. Again, we have covered this in a dedicated class as well. Just wanted to give a quick refresher. If you look at the final table, there is a many to many relationship here between books and genres. There is a one to many relationship here between users and check-in time. And then there is a one-to-one relationship here between users and the library card table over here. That's what the final basic schema would look like. Of course, a library management system can be much more complex, but great start. What you see in front of you covers all the 4 cases. One to many doesn't cover many to one, but as I said, it's just the opposite of one to many, and covers many to many over here and covers one to one over here. Given that, hopefully you understand relationships. Even though I don't know why I introduced this, they are not really needed in the next slide, but you should know them. Yeah, they're not directly needed, but if you don't know this, the next slide would be a little harder to understand. If you do know them, then should be slightly easier. Not straightforward. There are few new things to learn here, but yeah, you should know relationships. If you don't understand this, go back to the relationships class covers this in a little more detail and with some practical examples of foreign keys. Next up, let's understand how do you normalize data? How do you reduce redundancy in a database that has multiple types of relationships in tables? How do you find out if is there redundancy here, and how do you normalize the data? Alrighty, let's understand how do you know is your database normalized? How normalized it is? How do you quantify normalization? Thankfully, there are very nice metrics that you can follow to understand is your table 1NF normalized, 2NF normalized, so on and so forth. These are called normal forms, and the lower you are in this table, the better. If you've gone through a DBMS class, you've probably heard of them. If not, we'll go through each one of these, what they mean, and what are the rules for a database to follow for it to be 1 normalized, 2NF normalized, 3NF normalized, so on and so forth. Let's get right into it. Normalization in databases is a systematic approach of decomposing tables to eliminate data redundancy and improving data integrity. Two terms they've written: eliminate data redundancy and improve data integrity. We've already discussed what data redundancy means and why it comes into the picture. What does improving data integrity mean? Well, if you go back 2 slides, you might have remembered there is some data redundancy here. Harkirat name is present here as well as here, but there is also data inconsistency or the possibility of data inconsistency or data integrity to be lost. How? You can update the name of the user here by mistake, or let's say the user goes to their profile and changes the name from Harkirat to Kirat, but this change does not appear here. There are data integrity issues possible if you have redundant data. Normalization helps you get rid of these. The process typically progresses through various normal forms, each building on the last. It means you first reach the first normal form and then you build upon that to reach the second normal form, so on and so forth. When you look at a schema, you can identify if it lies in one of these categories: 1NF, 2NF, 3NF, BCNF, 4NF, and 5NF. You usually aim to reach 3NF. Basically, if you reach at this point, you are mostly good. You have enough normalization. Can you normalize further? Yes. But the more you normalize, if you looked here, it said it's a systematic approach of decomposing tables, which means if you have a table over here, it probably will be broken down into 2 smaller tables. That is what decomposing tables mean. And hence, the more you break your tables, the more you might have to join tables when users do queries, which is why you don't overly normalize, but reaching 3NF is sort of the bare minimum thing that you should do. Let's kick things off with 1NF. A single cell, these are the rules to follow if you want to call your database or specifically your schema 1NF normalized. Number 1, a single cell must not hold more than 1 value. This is called atomicity, and you need to hold atomicity in your database in case you want to call it 1NF normalized. What is an example of this? Let's say you're thinking of storing data like this, like we do in a NoSQL database. Here a student with ID 1 has this name, and these are the activities that they do. What is the problem in this? You might think like this is fine, just store an array here, but a bunch of problems emerge when you start to store data like this. One good example might be, how can you join this with another table where, basketball as an activity is present, considering there is no row here which has basketball as an activity. The row itself has comma separated values. How does the user search, okay, hey, who all currently have basketball as their activities? You will have to write a very complex query like this: select star from activities where activities like percentage basketball percentage. Like basically means if it looks like this, percentage basically means here as long as there is some data before and then basketball written and then some data after, then that specific row would succeed on this query. As you can already see, this becomes, much more difficult than doing a simple where activity is equal to basketball. So this is good. This is sort of bad, which is just a way to understand why 1NF is good. But generally, even if you don't understand it, this is the rule. The rule states, hey, if you have a table like this, break it down to look like this. There should be a column called activity, and you can have multiple entries here. Student 1 plays basketball, student 1 plays soccer, student 1 plays chess, student 2 plays drama club, 2 plays your book. That is fine. And now it follows the 1NF normalization. Now you can say this table is 1NF normalized. Here you cannot. This will be our goal throughout, to slowly follow some rules to reach 1NF normalization, then 2, then 3, and so on and so forth. So how is a table 1NF normalized? If you see multiple entries like this here, if you see non-atomic data, convert it into atomic data. That's rule number 1. Rule number 2, there must be a primary key for identification. This is thankfully generally true in Postgres. Can you attach primary keys to your tables? In this case, student ID can be a primary key for this table. Can it be? It cannot be. Student ID cannot be a primary key here because, as you can see, we have multiple rows for the same student ID. The primary key in this table would be a combination of student ID and activity, which means you will never have 2 rows which have student ID 1 and activity basketball. Just 1 row is good enough. What does the rule say? The rule says there should be a primary key. Now it can be a complex primary key like this one, student ID plus basketball, which is like an activity, is the primary key. Or it can be simple. For example, in this case, just the student ID is enough. Since we're shoving all the activities in a single row, just having the student ID here is good enough. Third rule, no duplicate rows. You should never have duplicated data, and that anyways doesn't happen if you have a primary key. Primary key by definition says that 2 rows cannot have the same primary key, which means, 2 rows will never be exactly the same since, primary key will change amongst them. And lastly, each column must have only one value for each row in the column. What does that mean? It says here, never shove data together. You might be tempted from time to time to do something like this. Customer ID 1 has this as the name, and their contact information is comma separated values which have email, phone number, address together. You might not break this down into multiple rows. Email is a separate row, phone number is a separate row, so on and so forth. This is bad. This again breaks 1NF normalization. Normalization says data needs to be atomic. Do not shove data together. That is bad for multiple reasons, similar to the ones we discussed in the first point. Here, if you have multiple comma separated values, they are much harder to search versus they are much easier to search if you have different rows with email and phone numbers. So this is how you would normalize this specific table. Have a separate field called email, have a separate field called phone number, and that is how you store your data. This is better than this, and they are different. Point 1 and point 4 are different. In point 1, we broke the data down into multiple rows. In point number 4, we're breaking the data down into multiple columns. That is what 1NF does. As long as your table follows these specific rules, you can safely say, okay, my table is 1NF normalized. This one's actually the easiest bit because we usually never do this anyways. Whenever we've created schemas until now, we have not done this mistake of shoving data together or, having arrays where you would want to have arrays in a NoSQL database. We have always had a table like this where we have had multiple rows that relate data rather than putting like an array together. And similarly, we've never done this. We've always had separate columns for, everything that's independent. We've never tried to shove data together, which is why this, most of the times, if you're creating a schema from first principles, it will almost guaranteed be normalized. If you're ever tempted to do something like this, just don't, because the whole point of normalization is to make your data less redundant. And as there is no real redundancy here, what it tries to get rid of is just grouping data together to avoid a bunch of complications later down the line if you're doing this. So avoid this. That's point number 1. Point number 2 is 2NF. This one gets rid of redundancy. Here we will see examples of how you can identify redundancy in a table and how you can fix it. Let's get right into it. All right, 2NF. While 1NF gets rid of repeating rows, 2NF gets rid of redundancy. A table is said to be in 2NF if it meets the following criteria. Number one, it is already in 1NF and it has 0 partial dependencies. We'll understand what partial dependencies are, but I hope we understand it only makes sense to optimize the tables further to reach 2NF if you have already first reached 1NF. So point one is always make sure my tables follow 1NF, and only then do you move to 2NF, the second normal form optimizations. And what does this say? It says that tables should have 0 partial dependencies. What is a partial dependency? Before we get there, do you see a problem in this table? Let's say, I don't share any information with you, don't officially share what second normal form means. Do you see any problem with this enrollments table where we store, this is a student ID that is enrolled in the course ID CS 101. The name of the course is this, the instructor name for the course is this, and the grade that this user got in this table specific course is A. Do you see a problem here? Do you see data redundancy? Computer science is coming twice. Why don't I store the course name in a separate table called courses? And then why don't I have a key between the enrollments table and the courses table? Why don't I have a foreign key constraint? Why doesn't my schema look like this? This is the student enrollment table, which it has the student ID. It also has the course ID that the user is enrolled in and the grade that the user got. And the course ID is a foreign key to the courses table, which looks something like this. It has a course ID, it has a title, it has a let's say, instructor, even though, instructor should also be present probably in a separate table called instructors or teachers, but you get the idea. When you build this from first principles, most probably you would have built it this way. Course is a separate table, so that in a single place you have that the course with ID 1 has title whatever CS and has instructor Harkirat, let's say, rather than having computer science the name repeated 2 places. This is exactly what data redundancy is, right? Computer science is stored 2 places. What if you want to change the name from computer science to computer science class? Then you have to go through this enrollments table through multiple rows and update it. Versus if you have a foreign key constraint to a courses table, you just change the title here and the updated title will appear for all the students that are linked to this specific course. So if you were building this from first principles, I would assume this is how you would have built it. But let's say you don't understand database design yet. You're not able to design your schemas and you built a very scrappy schema like this. How can you arrive at this solution? By using the rules of normalization. What is the rule of 2NF normalization? It says the table should have 0 partial dependencies. As long as you remove all the partial dependencies from your table, you will yourself reach 2 tables like this, and even through following rules you can improve your schema. But ideally, just looking at it from first principles, you should be able to understand data redundancy. Let me create a separate table called courses, and here is where I will store my data. What is a partial dependency? Before I've been saying partial dependency again and again. What is it? This occurs when a non-primary key attribute is dependent on a part of a composite primary key. This line, let's try to understand. What does it say? It says when a non-primary key, which means some key over here, if this is our table, let me bring this. When a non-primary key, what is a non-primary key? A key that is not the primary key of this table. As I said, a table can have composite primary keys, which means it can have more than one primary key. And in this case, a combination of student ID and course ID is the primary key for this table. If you look at this table, student ID plus course ID, which in this case is 001 plus CS 101, should be the primary key of this table. Harkirat, why not just student ID? Well, because you have repeated student IDs here. A single student can be part of multiple courses, can be enrolled in multiple courses. And what is a primary key? It needs to be unique for every row. This enrollments table doesn't need to store two entries for, oh, Harkirat has participated in CS 101. Just one is good enough, right? If Harkirat has done it once, that's all you need to know. Okay, Harkirat enrolled in CS 101. There is no point of having two rows like this, which is why what is the primary key of this table? It is a combination of student ID and course ID. So if someone asks, what is the primary key here? It's actually student ID, comma, course ID. These are the primary keys. Is this a composite primary key? Yes. If you have more than one column, that is part of the primary key. That is what makes it a composite primary key. And what does the rule say? That 2NF occurs. You can say that a table is second form normalized if a non-primary key, what is a non-primary key? All the rest of the keys that are present here is dependent on a part of the composite primary key. I repeat, partial dependency occurs if a non-primary key is dependent on a part of the composite primary key. Is course name dependent on either of student ID or course ID? Yes, the course name can always be inferred from course ID. If you ever say that this is CS 101 and the name is computer science, if I find CS 101 again, I can say, yeah, the name is computer science. Course name is always dependent on course ID. You cannot have two rows in which the course ID is CS 101, but the names are different. The names will be exactly the same. So do we have a partial dependency here? Is course name dependent on course ID? Yes. Is instructor name also dependent on course ID? Yes. Every course will have the same instructors. Again, if you have two rows with CS 101 written, the instructor name will be the same in both of them. So is there a partial dependency in this table? Yes. And what was the rule? It said it is said to be in 2NF if it has zero partial dependencies. Since we have two partial dependencies here, this table is not in 2NF normal form. You cannot say this table is 2NF normalized. How can you make it 2NF normalized? By breaking it down into two different tables. One called courses, where you have a course ID, course name, and instructor name. And second one called, let's say, students or enrollments, that this student ID is enrolled in this course and got this grade. Maybe this table is called grades. What is the primary key here? Here that is course ID. Okay, this is a course with this name and this instructor. Course ID is a primary key. What is the primary key here? It is a combination of student ID, course ID. Here every student ID plus course ID is unique. I can never have 001 CS 101 twice in this specific table. This is still a composite primary key, but are grades dependent on them partially? Is grade just dependent on course ID? No. There can be two different course IDs here with two different grades. Is grade just dependent on student? No. There could be two rows here where the grades are different for the same user. That isn't happening here. But if you look at this row, 2 has B also, 2 has again B. But it could have a C here as well, which means grade isn't partially dependent on the primary key. Grade doesn't depend either on course ID or on student ID. Grade depends on both of them. It fully depends on the primary key, which is why you can still say this is 2NF normalized. Instructor name could also live here. That really depends on you. Okay, where you think it makes sense for the instructor name to be. Well, it actually couldn't live here. My bad. No, this is the right place for an instructor name. All the details of a course exist here, including the instructor name. One thing you can do is, have a separate instructors table, which has the ID, the name, the age of the instructor, the years of experience, things like these. But this is fine as well. Yeah, if you do have that, is when again normalization will break. So let me, extend this example a bit. Firstly, let's understand this, and then let me extend this example a bit. What did we learn? We learned that something is in 2NF if it has 0 partial dependencies. What is a partial dependency? This is a partial dependency. Both course name and instructor name directly depend on CS 101, this thing right here. So we should just take this out into a separate table. If you have a partial dependency of 1 or 2 things on a specific ID, take this out into a separate table, and then the rest of the things can be related in a separate table, which is exactly what we did here, right? We took out what? Computer science and Dr. Smith, course name and instructor name, and the thing that you were dependent on in one table. And what did we do in the other table? Student ID, course ID, and grade. So we left student ID, course ID, and grade in the second table. Why is this good? Because we now have 0 partial dependencies. If you look at it, there is no partial dependency here. There is no partial dependency here. An extension of this is, if this had not just the instructor name, but a bunch of extra details about the instructor. The instructors table looks like this. The courses table looks like this. It has a course ID, it has a course name, it has a instructor name, it has a instructor age, it has a instructor year of experience. Let's say course ID 1 has course name Harkirat, CS, has instructor name Harkirat, has age, let's say 25, years of experience, let's say 5. Course ID 2, class is called physics, instructor is called Raman, years of experience is 4. Here, do you think this follows 2NF or does this not follow 2NF? What is the primary key here? Here it is still course ID. Yes, it is still course ID. So does this follow 2NF? Yes, it does. Since 2NF only makes sense if you have a composite primary key. If you have 2 things that are the primary key and not just one, which is why it cannot ever make sense here. If you have a course ID, which is the primary key, you can never have a partial dependency here. You will have a full dependency only. So this is actually fine. You might say, Harkirat, there will be some redundancy here. What if I do 3 and then DBMS, and then this is also done by Harkirat, and 25 and your experience 5. So Harkirat, there looks like there is some data redundancy here. You have 2 rows, row number 1 and row number 2, both repeating the details of Harkirat. This is the courses table. Why have you not taken out Harkirat in a separate table called instructors and have the instructor ID here to remove redundancy? Why is it? You have repeated data in this table. You to said this does not break 2NF. So how would I know? How would I follow some rules to break this down into a separate instructors table? And the answer is number 1. You can also, just how I figured it out, you also probably figured it out here. Harkirat is being repeated. It probably makes sense for these 3 rows, the instructor name, age, and year of experience, to be in the instructors table. And then eventually there should be a foreign key here. Instructor ID for this row is 1, and for this row is 2, and for this row is also 2. And then the name redundancy goes away. But is there a rule-based way to reach here? And the answer is yes. That is exactly what 3NF is. All right. Understanding 3NF. When a table is in 2NF, it eliminates repeating groups and redundancy, repeating groups by 1NF and then redundancy through 2NF, but it does not eliminate something called as the transitive partial dependency. If you remember in this example, I shared, even though this courses table has a primary key called course ID, and we have shoved the instructor data here directly. Instructor Harkirat is the instructor for course ID 1 as well as course ID 3. And we can clearly see some redundant data. Harkirat, name is present twice, age is present twice, if Harkirat ever changes their name or their age increases, this change will need to happen in two places. The years of experience will have to change in two places to maintain data integrity. But this is still in 2NF because there is no partial dependency. Why is that? Because the primary key itself is not composite. The primary key only is course ID. So there cannot be any partial dependency, because partial dependency, the definition itself says, okay, it should be partially dependent on the primary key. But if the primary key itself is a single row, there can be no partial relationships. Partials only make sense if you have more than one and then you depend on just one. Or if you have three, let's say, and you depend on two of them, then it is a partial dependency. But here there is no partial dependency. Let me change this a little bit. Actually, there needs to be an instructor ID here as well. Harkirat has the instructor ID of 1 and Raman has the instructor ID of 2, and then again Harkirat has the instructor ID of 1. This is what our table should ideally look like. There we go. This is what our table should look like. And as I said, there is no partial dependency here. But is there a transitive dependency, a transitive partial dependency in a relational database occurs when one non-key attribute indirectly depends on the primary key through another non-key attribute. Let me paste this here. What does it say? It says a transitive dependency occurs when a non-key attribute, okay, let's see what is a non-key attribute here. Instructor name seems like a non-key attribute because the key for this table is course ID, indirectly depends on the primary key through another non-key attribute. Can I say instructor name depends on instructor ID? If two rows have the same instructor ID, they will have the same instructor name. So instructor name directly depends on instructor ID. And can I say instructor ID directly depends on course ID? Since we know a course will have a single instructor, instructor name depends on instructor ID and instructor ID depends on the primary key. So can I say a non-key attribute indirectly depends on the primary key through another non-key attribute? The answer is yes. So here is where we cannot say it is in 3NF. It is not in 3NF because this partial dependency, not a partial dependency, a transitive dependency still exists in our database. And how would you fix it? Again, you would break it down into two separate tables, which is something you can again think from first principles. Here on the left, I would probably have the courses table, which has the course ID, course name, and instructor ID. And I would have another table called instructor, which would have, an instructor ID, name, age, years of experience. So here, now I can say the first row will have the first three parts here. And then the next three parts would be here. Something like this. And this, of course, is a foreign key over here. And then so on and so forth. You get the idea. The second row may, the name and the instructor ID would be here. And then the instructor ID, the name of the instructor and age and years of experience would be here. And this, as you can see, does get rid of data redundancy. Harkirat is now present, or the instructor details are now present in a single row. We don't have multiple records for the same instructor. We don't have the instructor name in two places, so that if the instructor ever changes their name, we don't have to change them in multiple places. There is no possibility of a data integrity issue. What if the instructor changes their name and you change it over here but forget to change it here, or the database crashes midway, whatever the reason might be. This can lead to data integrity issues. If you have it here, then everyone will have the name which is present here. If someone tries to update their name, if it succeeds, everyone will have the same name. If it fails, then everyone will still have the original name, but there won't be any data integrity issues. That is what now 3NF lets you achieve. And again, as I said, we just thought of this from first principles in the last part as well, right? Okay, clearly there is redundant data here, but now you can prove that there is redundant data. You can prove that this specific table is not in the third normal form, and you can convert it to the third normal form. Now, is name transitively dependent on instructor ID? No, it is directly dependent on instructor ID, which is the primary key here. Same for age, same for years of experience. Is course name directly dependent on course ID? No. Yes, it is. Is it transitively? No. Is instructor ID directly dependent on course ID? Yes. Is it transitively? No. So that's how you get rid of transitive dependencies. And once you do, if you have 0 transitive dependencies in your tables, is when you can say you have achieved 3NF. Here is another example. Let's say you have an employees database where you have the employee ID, the name of the employee, and the department details. Here, this employee is present in this department, where the name of the department is this, and the manager of the department is this. Here again, department name depends transitively on the employee ID. This employee will determine the department ID. There is a one-to-one relationship here. Okay, every employee ID will have a specific department ID, but the department name is directly dependent on department ID, which means it is transitively dependent on the employee ID, which again fails the rules of 3NF. How do you fix it? You break it down into 2 separate tables, an employees table as well as a departments table. That is how you would achieve 3NF, or the third normal form in normalization. This usually is good enough. You don't have to move beyond this. You can, but usually anything beyond this is asked in a DBMS exam in college. Usually you don't have to worry about going beyond this. You can, and then similarly there are slightly more complicated rules to reach BCNF, which is the next stage, and then 4NF and then 5NF. But either one of 3NF and BCNF is usually where you stop and don't normalize further, because 1, it gets a little complicated, and 2, normalizing more and more isn't always the best solution, because the more you normalize data, the more expensive joins you have, because you have to join more and more tables. You decompose a lot of tables, and hence when you want to join data, you have to join a lot of tables together, which can get expensive. All right, that's 3NF. Oh, and that's it for this slide. Cool. So yeah, what did we learn in this slide? Okay, when you're designing your schema, you can either from first principles figure out, is there redundant data in my tables, or you can use these rules, follow some rules to convert a non-normalized database or table into a normalized table, which is exactly what we have done here. Okay, if John Doe had 3 values here, we broke them down into 3 separate rows. If email and phone number was shoved into the same column over here, we broke them down into 2 separate rows, so on and so forth. For 2NF, if we know there is a direct dependency here partially to the primary key, which means there's a partial dependency, what do? You break it down into 2 separate tables, one for the courses and one for the enrollments. And lastly, if you know there is a transitive partial dependency, which means if a field depends on another field which depends on a primary key, then there's a transitive dependency. And if you have a transitive dependency, then you again break it down into 2 separate tables and get rid of it. That's how you reach 3NF. This is how you normalize tables. Should you follow these rules and figure out, am I to 1NF normalized on a pen and paper? Maybe, but does this intuition build fairly quickly? Yes. From first principles, you're able to figure out, okay, the name is appearing 2 places when I can just break it down into, a separate table. For example, here we were able to figure out, instructor name is sort of redundant. It's repeating in 2 places. So why not keep it in separate tables? That is what you're able to figure out and, go from there. That's all I had for normalization. There are more things we can cover if need be, but as I said, you rarely follow these rules. And usually just build schemas from first principles. So if there's something you want to do after this, is try to build a bunch of schemas for a social media application which has posts and likes. restrict yourself to SQL and then, create a Twitter like application and try to figure out, okay, how can I store the like count? How can I store the like relationships? How can I store the replies? Things like these, and go from there. If you want to look at a complicated schema, CMS has a fairly complicated schema because it has like nested folder structure. So if you open Prisma/schema.prisma, you'll see, the course content. Yeah, this is a fairly complicated schema to go through basically. Happy to explain, but again, the best way you would learn is, try to understand this whole thing together as to how we have created a recursive folder structure so that you can have a folder inside a folder inside a folder inside a video, and done it in a normalized fashion. With that, let's end it. I'll see you guys in the next one. Bye bye.